तो ये उस बारे में है, मतलब आज मैंने वो नहीं शुरू किया, लेकिन फिर वो कि नॉन यूक्लिडियन ज्योमेट्रीज। ठीक है, अच्छा तो so let us begin then. Okay, so I welcome all intellectual adventurers to this meeting. Today I'll talk about non-Euclidean geometries. So this will be a precursor to perhaps a future talk on general theory of relativity. So first, before talking about non-Euclidean geometries, is my voice audible?
Yeah, your voice is clear.
Okay, so before talking about non-Euclidean geometries, let us first talk about what is Euclidean geometry or geometry in general, because geometry and Euclidean geometry are kind of synonymous, because Euclid is so famous because of his book Elements. So this is the guy, Euclid, who wrote a book called Elements, and Elements is considered to be the one of the most read books in history. So perhaps after Bible, this is the most read book in history. So this contains of 13 books. So the first book starts with a lot of propositions or results related to geometry, circles, triangles, etc., etc. So first book also has, so it has definitions. For example, it says that a point is something which doesn't have any part, or in simpler words, it doesn't have any dimension. And another thing is a line is a length without breadth, as I mean some kind of common notions, some kind of very intuitive things. And apart from these, there are 5 assumptions, postulates, or axioms, as we call them these days. So this is it. Gyanti was calling me.
Okay.
Just a second. Will it also pause recording? I don't know. निखिल,
Yes, sir.
आप उनको एक बार लिंक भेज सकते हैं क्या?
हाँ भेज दो अभी. हाँ
ठीक है, अभी भेज दो फिर. Okay. And the next thing is, okay, so as I was saying, there are 5 postulates. So one of the postulates is that a line can be drawn between n given points. Let's say this is A, this is B. You can always draw a line between these points, and this is an assumption. Okay, and given a circle with radius something, let's say C, and radius R, you can always draw a circle. Okay, so but apart from this, there is also the famous fifth postulate. I said it famous because of the reasons that will follow now. Okay, so it says that if you have a straight, let's say if you have 2 straight lines, and there is one more straight line that is intersecting these 2 straight line at these points, let's say M and N, and on one side, let's say on this side, if the sum of the angles is less than 180 degrees, then if you extend these lines further, they will intersect, they have to intersect at one point. So this is the famous fifth postulate, and it created a lot of confusion as well as motivation in the community of mathematicians, geometers. So the thing was how to, or is it possible that you can prove this axiom or the postulate with the help of first 4? But okay, so this is the story that I'll talk in the forthcoming slides. But for the time being, I mean, this turned out to be a very, very important postulate. So apart from this, there are some common notions as well. So for example, one common notion is if you have, so this says that if you have A equal to B and B equal to C, then it follows that A is equal to C. Okay. So okay, so now let me take some examples from the elements. So Elements is a vast book and consisting of so many propositions, theorems, corollaries, etc., etc. So let me talk some of them now in order to appreciate what kind of reasoning it involved, what kind of simple reasoning and so elegant reasoning it involved. So I'll take a proposition from book 9 and that is proposition number 20. So proposition 20 of book 9 is about the prime numbers, that there are many infinite number of prime numbers. So and the proof goes in this way. So Nikhil, am I audible? Still audible?
Yes, sir, you are audible. Clear.
Okay, fine. Okay, so now we want to prove that there are infinite number of prime numbers. So this is how the proof goes. So we use it by using something called as reductio ad absurdum, or in common language, proof by contradiction. So this is a very famous and favorite tool of mathematicians. So they use it quite often. So they use this tool called the reductio ad absurdum quite often. So this is how the proof goes. So let us assume that there are finite number of prime numbers. So if there are finite number of prime numbers, and let Pn be the largest of them, because there are finite number, so there has to be some largest prime number. Okay, and now you make a number which is equal to the product of all the prime numbers is smaller than Pn, and you add 1 to them. So this is what you do. So P1, P2, P3, and Pn was the largest prime number, and you multiply all these prime numbers and add 1 to them, and you get another number n. So now what happens? So now there are two possibilities about this number n. So either this number is a prime. So for example, if you take the largest, this is only an example. If you take P n to be 2, so and if you do this, you will get 3. 3 is a prime. Very good. So and 2 into 3 plus 1 is also a prime. 2 into 3 into 5 plus 1 equal to 31 is also prime. So you get a contradiction because you said that this is the largest prime that you will have, but by doing this, you are getting even larger primes. So this is a contradiction. So since this is leading to a contradiction, your original assumption must be wrong. So this is how it is done. But there is one more possibility. So one more possibility is that the number you get after doing this multiplication is not prime. So for example, in this case, I'm sorry, I forgot to put +1 here.
Okay, +1.
Okay. So if you do this and if you add +1 to it, you will get 30031, but which is not prime, and which is equal to the product of 59 cross 509. But this number is larger than this. So because if a number is not prime, it should be written as a product of 2 primes, or at least 2 primes. So either this is a prime or this is not a prime. So if this is a prime, then it is a contradiction. And if it is not a prime, you can write it as a product of other primes, which were not there in the list before. So in either of the cases, you get a contradiction. So thus, there has to be an infinite number of prime numbers. Is this good enough? Is
Yes,
this
sir.
okay?
Yes, sir.
Okay, good. So okay, so this is one example from the Euclid, from the Euclid's elements, and there are so many. I mean, it's literally very extremely beautiful book to read. It's an extremely beautiful book to read. I mean, I have not read it completely, but I've read some of the chapters. No, not
Do you have the hard copy?
at one point of time I had, but now actually when I left IIT, I left all those books there.
Oh.
I do
So
not
this is Raghve, this is Euclid element.
Yeah, from the elements, yes, from the elements. So this is proposition 20 of book number 9.
Yes. So this is perhaps I just want to add one line as you have suggested. So every leading scientist used to admire this book. So even Einstein once said, if at all I have to go to an isolated place and to live for a long time, I will go with Euclid instead of either element.
Yeah. It is extremely beautiful book to read. I mean, it is so satisfying. Honestly, it is so satisfying.
Yeah, it's a foundation of many things.
Yeah, it is also kind of foundation of the modern mathematics, because modern mathematics works along this direction. So in modern mathematics, so whichever field you choose. So earlier they did not have axiomatized the probability theory, but Kolmogorov finally did that. So that is also an axiomatic theory. So now we have axiomatic theory of probability, and analysis is based upon 9 field axioms and so on. And linear vector spaces are also based upon 9 axioms. And finally, and also arithmetic. Arithmetic is based upon Peano's axioms and so on. So they have taken, I mean, so in that sense, the modern mathematics is kind of based upon what Euclid did about 300, not 300, but 2000,
2000 years
2300.
ago.
Okay. So yet another example from the Euclid is this. So that is proposition 32 of book 1. And I know this is very familiar to you because you must have seen this also. So this says that let ABC be any triangle, as I've shown here. So if you extend one of the sides, let's say you extend this side, and let's say this angle is AC and something. Okay, I should have put here D. So if this angle is ACD, then this is equal to the sum of opposite angles. So this is equal to the angle sum of this and this. So this is one part. Sorry, were you saying something?
No, sir, maybe some voice from my side. I will mute.
Okay, fine. So and the other part of it says, says that if you add all 3 angles, angle A, angle B, and angle C, you will get you will get 180 degrees. It will be equal to this. It will be equal to 180 degrees. Oh, I forgot to put it here. Anyway, but this somehow relies on the 5th postulate that we discussed some time ago. Okay, and so this was the original 5th postulate that if you have 2 lines and you have another line that intersects these 2 lines, and if the sum of the angles on either side of the line that was intersecting is less than 180 degrees, then if you extend the lines, they will intersect that side where the sum of the angles was less than 180 degrees. So there are equivalent version of the 5th axiom. So one is called as the Playfair axiom after a mathematician Playfair. So Playfair axiom is perhaps easier to grasp or easier to say in words. So what it says, if you have a straight line, let's say any straight line, and a point that is not on the straight line, you can draw one and only one straight line that passes through that point. Okay, I'll show it next. Okay, so let us, because 5th postulate is so important, let us talk a bit more about the 5th postulate. So okay, so as I just said, it is so an equivalent statement of the 5th postulate is called the Playfair axiom. So geometers really tried hard to prove for the 5th postulate of the axiom from the first 4, but they miserably failed because it was not possible. They found that it was not possible, and 5th postulate is a separate logical possibility. But their effort really paid a lot because that ultimately led to something called as non-Euclidean geometries, as we will discuss in the forthcoming slides now. So one example of non-Euclidean geometry is a geometry of constant positive curvature. So of course I have not defined curvature, but curvature can be intuitively taken as departure from Euclideanness, if I can say that, because in case of Euclidean geometry, the sum of 3 angles of a triangle is always 180. But as I will show in the next in the forthcoming slides, it is not true in the case of, for example, sphere or other geometries that I will also speak about. So, but so this example was known for a long time, but this took really some time in order to be discovered. So this was about 1850s or so, 1850s or 1860s. So 3 persons, Gauss, Carl Friedrich Gauss, the prince of mathematicians, Carl Friedrich Gauss, and Janos Bolyai and Lobachevsky. So these were the 3 mathematicians. So, and they separately did that. So their research was, just a second, let me put my, okay. Am I still audible?
Yes, sir.
Okay, now it's better. Now it's way better. Okay, so and another example was surfaces of constant negative curvature. So one way of realizing, I mean, so this is an example, or rather, okay, so this is an example, or perhaps the only example that I'm not sure about, but this is an example of a surface which has constant negative curvature. So this was the case when you have constant positive curvature, but in this case you have constant negative curvature. So how do you get this? So this is the parameterization of this curve t. So this is x coordinate, this is the y coordinate. So if you plot it as you vary t, you will get this, and if you rotate it about this x axis, you will get this. Okay, so although, and one more thing is, although it appears that it kind of terminates at this point, but this is not, because this goes till infinity. This never ends. So these are not the terminal points. Okay, and this continues till infinity. So, and these were the three persons, as I was talking about: Carl Friedrich Gauss, Janos Bolyai, and Nikolai Lobachevsky. So a German, Austrian, and a Russian. So these persons independently discovered this example of constant negative curvature. I mean, this, and it is, we also call it as a pseudosphere, because a sphere has a positive curvature, a pseudosphere has a negative curvature. So okay, so one thing is, I mean, so now since we know a bit about that the fifth axiom does not hold, so we perhaps need to do our geometry a bit carefully. So why by carefully I mean, so we have to have precise notions of straight lines, circles, etc., etc. So let us try to do it, the geometry, a bit more carefully by relying on just the definitions, because if we rely on the definitions, that or perhaps only the logic, so of course intuition is very important, but sometimes intuition may deceive us. So it's it's better that you should somehow, how to say that, uh, convince yourself with the help of logic as well. So now in these cases we will consider, so because we will always, because the 3D cases are very complicated in order to imagine. So we'll start with just the 2D cases. So these are the cases in which bug is studying the surface on which the bug is lying. So here I've shown the bug that will try to study the properties of the surface on which it is lying. It cannot look upward, and it cannot really take help from, let's say, navigation satellites, etc., etc. Okay.
Hello?
Yeah. Fine. So okay. So now we have the basic geometrical notions. So one is drawing straight lines. Like how do we draw straight lines? So, and we will show next, or we'll discuss next how we do this. So the idea is, take 2 points A and B, say any 2 points A and B, and find a curve of shortest distance between them. So this is how you draw a straight line. And how would you draw a circle? So for that you fix some point which is called the center, and then you mark points at equal distance from that center C, and you just join all those points, then you will get a circle. And also you can, so once you know how to draw straight lines, you have to just fix 3 points, and then with the help of because you know how to draw straight lines, you can draw triangles as well. So now, and yes, and then we will also see how to draw parallel lines, because so this is one more difference. So as we will see that because this was a version of Playfair axiom. So what I said was that if you have a straight line and a point that is not on the line, you can only have one parallel line. But as we will see, this won't be true for the elliptic geometry and the hyperbolic geometry, as we will see. Okay, so now let us start with the plane geometry, the usual plane geometry that we are very much aware of, very much familiar with. So now, how would you draw a straight line? So for that, you will take 2 points, let's say here, which has the coordinate of -3, -4, and this is 5, 2. And then you just draw a straight line, because you just use straight edge and just use your pencil and draw a straight line. Okay, and now how would you draw a circle? So let's say you have this point fixed C, which is the center at -1, -1. Okay, and then you mark 4 points which are equally distant from it. So 1, 2, 3, 4. These points are equally distant from this point, and then you just join all these points smoothly. You get a circle. So, but there is a peculiar thing, or not rather peculiar, but a pattern in all the circles. So although you may draw very big circles, very small circles, whatever, but then all of the circles will satisfy one property, that the relation between this length, the total length of the perimeter, and the radius will always satisfy a given relation, which is this. So there will always be a fixed ratio between circumference and the radius. So this is very important aspect of plane geometry. You will always find this. And next, how would you draw triangles? So for that, you will fix 3 points, let's say A, B, C, and you just draw, because you now know how to draw straight lines. You can take 3 points and you just draw the straight lines. And it turns out that the sum of the angles in all the triangles, in whatever triangle you make, it can be isosceles, it can be scalene triangle, it can be equilateral triangle, but the sum of the angles is always equal to 180 degrees. And how would you draw parallel lines? I mean, okay, of course there's a way of constructing parallel lines as well, but let us not go into that, because you can, if you want to, you can have a look at it in any geometry book, or maybe I can say something about that. Okay, so but the point is that you will have only one parallel line, not more than that. So if you try to tilt this line, it will eventually intersect. So that's not the point. I mean, so the point is not how to draw the line, but the thing is that there can only be one straight line. Okay, so but okay, so this was the case for plane geometry, but now let us see what happens, or what differences are there in the case of elliptic geometry. Okay, so let's draw a straight line. So one example of elliptic geometry would be the geometry that you would do on the surface of a sphere. So now let us draw a straight line. So you fix 2 points here again. So let's say here and here, and but now the straight line would be along the surface. It will not go through the surface, because as you remember, the work can only, because we are doing all the geometry with respect to, or the bug that can move only on the surface. It cannot go upward, it cannot go inward. So this is the shortest line that is on the surface, and this line lies on the great circle. So if you assume that this is a longitude, let's say this is longitude, this is north pole, and this is south pole. So this line, so this is a kind of circle that passes through the north pole and the south pole, and this is the intersection, and the circle is the intersection of the sphere and the plane that passes through the center, north pole and the south pole. So this line lies on the intersection of that plane and the sphere. Okay, so now you know how to draw a straight line. But okay, one possibility could have been this. I mean, in this way. I'm not able to show it here, but you can imagine what I'm saying. But that would not have been that would not have the shortest length. So because in that case the length would have been more as compared to this case. Okay, so now how would you draw a circle? So for circle, let's say you fix a point, because now we are using the definition. So you fix a point, let's say this is your point, and then you measure distances which are equally distant from this point, here, 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 here. So all these points are equally distant from this point, and you join all these curves, all these other points smoothly, and then you get a circle. So now you see some peculiar property of this circle. So this circle has different property from what we had in the plane geometry case. In this case, you will find this relation to be true, that the circumference is always less than 2 pi r. And why is this true? As you can imagine, because as you can imagine, this I mean, okay, so I should have taken that diagram as well. Okay, so let's say this is a circle, but how to say that? Okay,
So okay, I should have put a picture, but anyway, okay. So I'll explain it in some other day, because it would not be easy to explain, because I have to make some, or maybe I'll explain it in the end with the help of some diagram. Okay. So now how would you draw triangles? So here we learn how to draw straight lines. So one thing to be remember is that you have to put your straight lines only on the great circles, so they cannot be elsewhere. So once you have, let's say, got three points, one is on the North Pole, and these two are on the equator. So now you just join them together in this way, and this line will lie along the great circle. That is a circle which is on the intersection of this sphere and a plane that passes through the center and these 2 points. Is this clear? Am I audible?
Yes, sir. Yes, sir. You are clear, sir.
And is this clear what I'm saying here?
Yeah, I'm trying to.
Okay. No, so the thing is that okay, for this case, so you should always think about great circles. So great circles are the circles which are obtained when you intersect the sphere, the whole sphere, and a plane that passes through, let's say, these 2 points and the center. So 3 points will uniquely determine a plane. So you will get this. Okay, I should have also put a picture, but okay, anyway. So this line will lie on that circle, and this circle is known as the great circle, because this will have the greatest possible radius. Because if you think, so you could have said that, why not this? Let's say, why not this? But this won't be having the shortest distance. So this won't qualify as a straight line as per our definition. But in this case, you will find, so in the case of plane geometry, you found that the sum of the angles is always equal to 180 degrees. But in this case, you will find that the sum is always greater than 180 degrees, as you can see here, because you see, these are almost 90-degree angles. So this is 90, this is almost 90, this is almost 90. So, or maybe perhaps let's say 80. So if you add 80 plus 80 plus 80, you will get 240, which is definitely larger than 180. So in this case, all the triangles will have to have the sum greater than 180 degrees. And the larger the triangle, the larger will be the departure from 180 degrees. As you can show, if you do some math, it should be easy to show. Or there are results available already. You don't have to derive them, just have a look at them. And now, how about drawing a parallel line? So let's say this is the line that runs from North Pole to South Pole, and this is the point through which we want to draw a parallel line. But is any parallel line possible? Can anyone say the answer to me?
No, I don't think so. I don't.
Yeah, because it will always interact. It will always intersect at North Pole and South Pole.
But one thing.
Yes.
If at all this circle has the radius of let's suppose edge of the universe, so by the time they will intersect at the edge, right?
Sorry, what was that?
Let's suppose the radius of this great circle is the edge of the universe.
Or you mean the radius equal to the visible what?
Yes. At least
visible universe. Okay.
Visible universe. Okay. So by the time let's suppose we will draw two line. Of course, in principle they will converge at the point when what is that called? North Pole or South Pole. Okay. But now imagine if you are actually treating it like much bigger great circle or a sphere. So the parallel line will intersect at the edge of the universe, and they will feel like. But I think the angle between them will change, right? So concept of parallelism never exists in this curve geometry.
Yeah. So I did not get your question. What you're asking, I did not get your question.
What I'm telling, the concept of parallelism or the existence of two parallel line, I think don't exist in principle in this kind of geometry.
Yeah,
right?
yeah, yeah. So this is what I'm saying, because it will always, because this will be the straight line that passes through this point and it will intersect at north and south pole.
If you can see also, if it doesn't intersect also, if you see the point to point, the distance between two lines actually it does vary.
Mm-hmm.
No, parallel lines means the distance between two lines has to be remain fixed.
No,
No
no, that
matter
is not true.
whatever.
That is not true. I mean, that is perhaps, so that is an extra assumption, or that is something extra that comes in the case of plane geometry, but it is not true in general.
No, I mean what I'm trying to say. If you
Okay.
see, Rahul, can you see my cursor?
I can, no, I
In
cannot
the
see.
last great circle.
Okay, okay.
Okay, so you have drawn a line and you are asking for the parallel lines.
Mm-hmm.
Okay. So now if you see, let's suppose in plane geometry or Euclidean geometry, we used to call two lines are parallel, provided the distance between them remain constant.
No, you see, you have to understand one thing here. I mean, perhaps in the case of Euclidean geometry, the parallelism will imply this, but this is not the universal definition of parallelism.
Exactly. But here, one criteria you are saying that is correct, of course, that if you see two lines, they will meet either at a north pole or south pole. Correct. But from the great sphere, sorry, that is called great circle. If you just go just to 1 centimeter up or 1 centimeter down or 1 kilometer up or 1 kilometer down, the distance between them also varies. That says actually they are converging, right?
Okay.
So from that cannot we conclude? Do we need to see the end point?
Yeah, that may be, because as you will see in the case of hyperbolic geometry, the distance can also change there. But yes, in that case, the distance always increases as you move away from the point. So yes.
What I mean to say, it will not remain constant immediately. If you, however small may be the variation on the line, if you just go up or down by kilometer or meter or centimeter, you won't find the distance between two lines remain fixed. It will change. Either it may increase or decrease, whatever may be the amount.
Okay.
No, that's what I'm saying. So that also can be another indication to see. Of course, we are not on the Euclidean geometry.
Okay. Yeah. Yeah. Fine. I mean, so then you have to add one more add one more detail to it, that it's not just that the distance between the let's say the line changes as you move away from the point. It's
Okay.
you also have to say that the distance should increase if the line were to be parallel. If the lines were parallel, the distance should, as you will see next, because in this case the distance is decreasing, but in the case,
Decreasing, yes.
oh sorry, I'm sorry, I meant, yeah, in this case the distance is decreasing, but in,
Yes.
so yeah, so eventually they will meet at some point, but that won't
Yeah.
happen in the
And
case of hyperbolic geometry, because in that case
they
also,
will recede away from each other.
yeah, okay,
Okay.
fine.
So positive geometry case.
Yeah, and so this is positive curvature case and that is negative one. Okay.
Yes. Okay.
Fine. So in this case, as we saw that there are no parallel lines. But now what happens in the case of hyperbolic geometry? So hyperbolic geometry is a bit difficult to imagine, but then many mathematicians have come up with a model. So this is known as a Poincare disk. So we'll consider this example. So this is something called as a Poincare disk. So in that case, what happens, that this boundary, so this boundary represents infinity. So you can see infinity here, okay? And this is the center of this circle, and the boundary represents infinity. And the objective is to find out a line that is that goes through P and Q. Okay. So now we will show the construction of drawing a line that passes through P and Q, because as we said before, that this is the most basic requirement of a geometry, that if you are given 2 points, you must have a way of drawing line through them. Okay. Okay, so how would you do that? And yes, there is one more requirement. I mean, perhaps this comes from the mathematics itself. I mean, I'm not so sure about that, so I cannot justify at least it right now. So one more requirement is that all the lines. So let's say any line that you will draw, let's say passes through a point P, must intersect orthogonally. So and as I will say, okay. So let's say a line, there's a point P here, and you have a line that passes through this. So this angle should be 90 degrees. Okay, this is the requirement. I mean, I'm not sure how this requirement comes about, but okay, at least not now, I'm sure. But I should read about it, and I will let you know later. Okay, so now let us see the steps of making a straight line. So first step is you draw. So this is center, and these are any 2 points. So this angle will be 90 degree by default, because these are normals. Because we know in the case of circle, all normals pass through the center of the circle. In the case of circle, because circle is a very special kind of curve. Okay, so let's say, and although I've not written down, let's say these points are M and N. Let's say this is M, this is N. So from M and N, now draw tangents. So these are the tangents. So this is tangent 1, this is tangent 2, and let's say these meet at some point S. This is the point S, and now from S you draw a circle which passes through both P and Q. So in this way. So this is a circle that has P and Q on its circumference and S as its center, and now your line is this. So by construction, we have ensured that this angle is 90 degree, and this is your straight line in the case of hyperbolic geometry. Okay, so once you know how to make straight lines, and similarly you can also use the the relation or the definition of drawing circles as well. So now once you have once you know how to make straight lines, you can draw triangles, etc. And if you do that, you will find that the sum of the three angles of a triangle is always less than 180 degrees. Okay, and for the case of circumference, this is what you will find, that the circumference is always greater than 2 pi r, as you can check, and the sum of the angles of a triangle is always less than 180 degrees, and there are infinite number of parallel lines. So for example, so one line can be this. I mean, this is not exactly perpendicular, but this is kind of geometrical problem, but yes, but you can do this. So this is one line. So let's say this is the line, and this is the point that is not on the line, and we want to draw parallel line to this. So because this is infinity, they cannot go anywhere, and this is a line, this is a valid line. So one line is this is another line, this one, and this one is another line which passes through this. So these are all parallel line to this. So you can have infinite number of parallel lines. Okay, so okay, so now let us summarize and conclude what we discussed.
Rahul, before you summarize, so I just want to ask a small thing. Can you go back?
Okay.
No, you have drew some parallel lines. Yeah, small circles. Okay. So clearly, in the context of physics, we'll be discussing this in terms of the curvature. Okay. So still, though we are studying it in the abstract viewpoint, but if you just consider two things, suppose you are living in a curved universe or a curved space-time, and scattering is happening. And if suppose the scattered particles are simply following the trajectory based on the curvature they are actually residing in, okay, cannot they actually give us the hints that what is the nature of the curvature of space-time the scattering has happened? Let's suppose, as you said, it is the circumference of the circle or the sum of the angle of triangles. They essentially decides whether it is positive curved geometry or negative curved geometry.
Okay.
I suppose two particles get scattered with each other, and they simply follow the trajectory based upon the space-time. Okay, they cannot randomly move, man.
Okay.
So depending upon this angle of incident and angle of scattering, so cannot we actually draw any sort of hints or indication that what sort of geometry actually upon which the scattering event has taken place?
So, so if I'm correct, I mean, if I get a question correctly, then
Yeah.
so perhaps so please confirm. I mean, so there's one more way of simplifying your question. So
Okay.
so one way. I mean, why look at the particles? Perhaps one more way or perhaps a better way is to just draw very large triangles and to see whether the sum of the triangles of a triangle is 180 degree or not.
That is perfect. That is perfect. But I'm just saying for the sake of curiosity, let's say many uncountable scattering event is going on. So let's suppose you are studying it in a more details. Let's suppose in SORM or Formula, whatever it is. So we're calculating this Weinberg angle, fixed mechanism, and all that. So cannot information about the space-time be known from that event?
It's very unlikely, because you see, I mean, so the information of space-time will okay. So now, as we know that according to general relativity, the space-time gets modified because of the presence of matter and mass in it. So
That's right.
so it may get modified. It will be modified, but the modification is so small that it is barely detectable, because the most of the effect will be because of Earth's gravitational force, or because of Earth's gravity. That would be very small at any rate. So how would you even see that? How would you even detect that?
Yeah, whatever you said, it is a challenge from the technical side. I means our precision problem.
Mhm.
But in principle, we can get any sort of information regarding the background space-time, right, on which event is occurring, based
Yeah,
on
it
the
is possible, but yeah,
yeah.
I guess in principle it should be possible. I mean, so one easy way would be to just see how much a photon deflects so let's say you are pointing a laser in the horizontal direction, and the laser is propagating, or the photons are propagating, and by the deflection that happens to the laser at some distance, you can also infer something about Earth's gravity. So
Yeah.
that is one possibility.
So finally, okay. Maybe since we have a lot of theoretical and experimental knowledge right now in favor of GTR, so it may feel like or seems like it's an easy-going problem, but during the early stage of GTR, or by the time this concept would have been developed, since means before 2000 years ago or so. So it would have been an incredible way of studying the space-time along this line.
Yeah, so I mean, one very easy way of doing it is to so you do the geometry on the surface of the Earth. Okay, so then you okay. Actually, I taught this at UWC. I
Oh,
taught
I
this
see.
part at UWC.
Great.
So I'm not able to recall what I said there. Okay, so one way of actually detecting whether the surface of Earth is curved or not, you just draw big circles on the surface of the Earth, and you measure their radius. Okay, and then you can also, I mean, I'm not able to recall it right now. Let me think of it. Oh yes, fine. Also, yeah. So this is how it goes. So okay, so you can measure two things. You fix a point. Let's say you fix a point on the surface of the Earth, and then you draw a circle, a very large circle. Let's say 20 kilometers of radius. So the circle has 20 kilometers of radius, and then you draw a very large circumference. So first of all, you have to somehow arrange 20-kilometer long rope. Then only you can do this. So the radius is 20 kilometers, and then you can also measure the periphery, the circumference. You will you will find a deviation between the two. I mean, so the circumference should have been 2 pi r, but you will not. But if you do the math correctly, if you do the math there, you will find that the circumference that you find for the circle is not equal to 2 pi r. So then it will give you indication that that the surface you are living in is curved.
But one question then I would like to ask, maybe I just like to refresh my school knowledge. That by the time this element was discovered or written down by Euclid, people used to give the ideal example. How do you know that the surface of Earth is curved, not sphere, not flat? They used to give you many example like you can see the masthead of the flag of the ship from a very distant sea. So that is an indication clearly. This is a school thing knowledge. So this kind of concept, why haven't they used then?
Sorry, and this kind of what was not done?
No, as you said, the experiment is very simple because there are some desert which actually stretches hundreds of kilometers, right?
Okay.
So people can very well would have gone there and drawn a circle of 20-kilometer radius. It's not a big deal. But will it give the indication that the sea is less than, of course, less than 2 pi r? So they would have confirmed there itself before 2000 years ago.
Yeah, perhaps it's not worth the pain, because first of all you have to
Okay.
arrange. I mean, we are happy. We are not much concerned about the geometry of the Earth.
Okay. I just why did I ask this question? Because this is how we have taught actually taught in the school and intermediate colleges. People used to ask me, the science teacher used to ask you the question: how do you know that surface the Earth is spherical? So we used to see now from a distance. From a distance, we can see the top portion of a ship in the deep sea while it is approaching to the shore. That says the shape of the Earth is not flat. Instead, it is curved. So why do I need to wait for a ship to appear in a big deep sea? I could have gone very well to the desert if at all I am staying in, let's say, for that pyramid, that area. I could have drawn a circle of 20 kilometers and would have measured and the triangle also. Any
true.
sort of thing would have done.
Yeah.
And this thing is so simple because by then I don't know what was the standard of voyage, because she could not have been in the concept of in the dream.
Actually, in this regard, perhaps a Greek mathematician, Eratosthenes. So there was a Greek mathematician called Eratosthenes.
Yeah. I have heard about his name. This.
Yeah. So he actually knew,
Eratosthenes.
and based on this only, he kind of calculated the Earth radius. So, I mean, he actually used. Okay. I mean, I'm not able to recall the exact experiment, but then he could calculate the Earth's radius by seeing the shadow. That okay. So this is. No, I'm not able to recall the exact experiment, but this is how it was like. So Eratosthenes was a Greek mathematician. So you have two different places, and at one on some day the shadow of the sun, or rather the sunlight of the sun should fall directly to the wall, but it does not happen all the time. So I mean, or maybe not in so okay, how to say that? Okay, so because if it is along the radius, if it is along the radial direction, then only you can see sun's reflection on the water of the well. But if the surface of the Earth was all flat all over, you would have seen it in all the wells.
Yeah.
Kind of.
Yes. I understood. So that's a sort of projection of the sphere on a Euclidean plane, like a circle. They used to see. No, whatever you are saying, I am just telling that.
No,
and in fact, by using this method, probably Roman has calculated the speed of light also by using similar sort of argument.
Okay.
Maybe. Exactly.
Maybe.
Yeah, because he used to actually investigate the Jupiter eclipse, solar eclipse in Jupiter, something like that. So by using that only, he used 4 moons of the Jupiter to calculate the speed of light for first time.
Okay. Oh yeah. I've heard about that experiment.
Yeah, like this. He also draw some geometry on the flat land on sand only, and he made it, putting some stones, 4 stones around the sun, and he did calculate with an incredible accuracy as far as that time technology is concerned.
Okay, so since I'm talking about it, so let's say here is the sun, and if this and so here if there is a well, you will see the shadow of the well, sorry, shadow of the sun in this well, but you will also see the shadow here if the surface was flat. But since this is curved,
Right,
you will see the shadow or the sun reflection here, but not here.
right.
Yeah. So yeah, so the argument was something like this. I mean, perhaps it's not exactly what he said, but he also calculated the radius of the Earth using this.
But another thing, had it been the flat surface, let's suppose Earth is a flat one, then it could have got a plane kind of thing. Na? It's a rectangular parallelogram or something like that.
Okay.
But while you observe the shadow of the Earth, it is spherical.
Sorry, it is
I
what?
mean, let's suppose I have a rectangular plane or parallel plane. So if I actually create a shadow by shining light on it, so what kind of shadow I will get? I will get the flat image, right?
Okay.
Flat. But when Earth's shadow we can feel, we are actually seeing it in spherical in nature. Na? So though it is a circle, it's a projection of 3D onto 2D, but it is spherical.
Sorry, so there was a bit of noise in the background, so I could not understand what you said. So I'm sorry, could you please say that again?
Yeah. Here, whatever you said, that is correct. But let's suppose, imagine there is a flat plane or any sort of wood, a flat actually, Euclidean.
Flat plane, okay, flat plane, okay.
Okay, so what sort of shadow one can expect? It's a flat image only, flat shadow.
Of sun or
Right?
what object? Sun.
No, Earth.
Oh, flat object on moon then. You are you saying you will watch lunar eclipses or solar eclipses? Oh, sorry, I'm sorry, lunar eclipses.
Yeah.
Okay.
So, but this is not the case. So that is also another confirmation. Earth is not flat. This is very.
But that was not actually true, because at that point of time they had some different notions of eclipses.
I see. Oh, why then Copernicus theory was not in the time. Okay.
Yeah, I mean, at least in Indian context, they would say that there are demons, Rahu and Ketu.
Geocentric, they were believing in geocentric, like
not just that, but I'm not sure. I'm not sure whether they had the right notion of what eclipses are or what cause eclipses.
And they did not have the idea of a solar system. They did not have clear-cut idea of solar system. Right. Yeah.
I mean, you don't have to have the clear-cut idea of solar system, and for that matter, but you have, but you should have, because we are seeing, let's say, solar eclipses. For solar eclipses, you just have to understand moon, earth, and the sun system, and for the and also for the lunar eclipse. But I'm not so sure whether they knew the mechanism, like how is this happening, how is that happening.
Because it is understood, they did not know it because they did not resolve the solar system arrangement.
I'm not so sure about that. That they actually knew it, because so perhaps maybe after Renaissance, let's say in the 15th or 14th century Europe, only they knew about the mechanism. But I'm not so sure. I have to check it. I'm not sure about that. So yeah, based on that, so given that the mechanism is not clear, you won't be able to attribute the circular image on the moon to the circular image of the.
One thing I want to ask. So 1610, if I can remember correctly, 1610, I think is the year on which Kepler discovered his style law.
Okay.
1610.
Okay.
So you are saying by 1500 century, would they have any idea, or they would have any idea the people would have conceived what is the mechanism of the solar eclipse or lunar eclipse and all that?
I mean, I'm not saying something very exact here, but then
No,
but then earlier we were
I'm
talking
also
about BCs. So at least this should, so when I'm saying that this idea was not clear, I'm really talking about BCs before,
Okay, I see.
let's say some 200 BC or maybe 100, 180, 280.
Okay.
Certainly during not that, certainly not during that
They
time.
must, I think they must be not be knowing the exact mechanism. There might be some speculation, but the solar system was clearly resolved only after Kepler's law came into picture.
Mhm.
Is it not? What the celestial mechanics taught us?
No, that is true, but then it has nothing to do with the solar system, in my opinion. I mean, it has to do, it has to do with the fact that first of all, the shape of the Earth is spherical, and somehow Earth comes in between Moon and the Sun, or Moon comes in between Sun and the Earth. So that's how eclipses happen.
Yeah, but if they would have actually skipped those mechanism part, saying somehow it would have happened, maybe they would have some vague idea of how the thing is going on. But what I'm saying, the exact quantification or the perfect repeatability of the data or prediction had occurred after the prediction of or discovery of Kepler's laws. I think that's what the historian says.
Or maybe after the discovery of Newton's law of gravitation.
That explains the mechanism. That explains the mechanism. But the proper arrangement of the heavenly bodies actually somehow got finalized after the Copernicus theory came into picture and followed by Kepler and Tycho, all those things.
Okay.
Maybe it's a lot of historical debate who come first, who came second. But
Yes, sir.
anyway, mechanism still today also there are some mysteries. So anyway, I just asked for the sake of my curiosity.
Thank you for the question.
Why haven't they gone to the desert to measure it?
Yeah, because I mean, so this is what I can think of, because it was perhaps not worth the effort. Why would you make 20 kilometers long rope, 30 kilometers long rope, just to know what is the geometry of the Earth? There are some more important questions to be answered.
At least they were mostly inclined towards the money making and rule the world.
Maybe not even that, but then perhaps there are other important issues. So it really depends. So if so we really pursue those things which we feel are important.
Exactly. This is the most precious statement. This is the most precious statement. Ultimately, this is the statement which decides the destiny of any social society in a given time.
Yeah, that is true. I mean, so because
This is the statement.
I mean, so perhaps this is not related to this talk then, but the Aristotle had his what the school of logic. There were also Stoicism, and there were so many schools of thought, and at that time, because perhaps society needed them, and that's why they were invented. We also had some Aristotelian laws of motion. I mean, maybe he was just curious to know why motion happens, or can we quantify motion, and so on. But it depends whether you feel whether it is useful or not. If you don't feel it useful and important, you will not
Okay.
pursue it.
I'll just ask you a funny question, because the day before yesterday in IOP, I had a discussion with one postdoc. So in those days, the days what we were talking about, Aristotle and all those natural philosophers, of course, not scientists. So those people used to believe actually things moves for some time and then stops because body gets tired. Okay.
Kind of,
So
yes.
this is how the history of motion began. And now also we are saying system actually always try to minimize its energy so that it remain in a much stable state. So it is not the same thing, but spoken in a different style.
I mean, and also the gravity theory
I'm
included.
asking. I just want to know your view on this.
I think I also have heard about that. What was the name of the book? So there is one book which was forwarded by Ed Witten.
Written, okay.
Yeah, that was forwarded by him, though not written by him, but forwarded by him. I'm not able to recall the name of the book, but I think in that book a lot of history is covered. So one part that I'm sure about is that Aristotle used to believe that so why would object fall downward? Because it will, there's a kind of bond between Earth and that object. And why it accelerates? Because as it is falling and it is going towards the center of the Earth, it is becoming more and more excited, more and more enthralled, something of that sort. So that's why
Like
it will
that, like
accelerate.
that. Yeah. Like that only he mentioned this statement. He said that now we are saying every system try to minimize its energy and to remain in the stable configuration of system state of energy. So that is what they have told 2000 years before. Body try to take rest. That is why it doesn't move always uniformly, or it doesn't try to keep on moving.
Yeah, sure. Okay.
But I think
So
the fiction can. Okay.
yeah, so whatever we discussed today were the cases of 2D surfaces. I mean, if you were to go to 3D, these will be quite, I mean, perhaps very difficult to imagine. So but then 2D would give example or the feeling that what we would do in case of 3D. So there is one more technique which is called as the parallel transfer, which we have not discussed about today, and this is also useful to tell you whether the space in which you are in is curved or not. So curved is, we say something, if some space is curved if it does not follow the rules or the axioms of the Euclidean geometry. But in whatever case you take, if you take very small region, so here I should have put very in quotes, because so the smaller the region, the more it will approach towards the Euclidean case. So if you recall the example of the sphere on the surface of, sorry, if you recall the example of triangle on the surface of the sphere, if you just shrink the size of the triangle, the sum of the triangles will approach to 180 degrees, as you can check. I mean, of course, you can check it on the surface of the Earth, because we cannot make so large triangles. So because the surface of the Earth can be very well approximated in a very small region as the plane. So whatever triangle you draw, you will always get sum of its triangle equal to 180 degrees. So this idea, the idea of a manifold, which we have also not talked about today, generalizes the notion of surfaces to higher dimensions, because manifolds are some kind of mathematical objects which locally look like flat spaces. When you talk about very small regions, I mean, of course, these have precise mathematical meanings, and these perhaps can be talked about in future talks. So then this, I mean, in this context, the general theory of relativity states that in the presence of matter and energy. So I've talked about the manifold, the space-time. So here we use the notion of a space-time manifold. So in the presence of matter and energy, the space-time manifold become curved. So yeah, maybe we will talk more about general relativity itself. So and I will also try to reduce the number of equations in it, because that is also true. If you don't really use math in it, it is my opinion, if you are studying general relativity, then perhaps you won't understand or you won't take anything out of it. I mean, so some math is kind of inevitable in it. So you have to introduce kind of tensor, or but when you talk about the equivalence principle, etc., equivalence of constant acceleration and gravitational fields, then that's a different story. But then if you were to get some numbers out, math is inevitable. Okay, so see, these are the references I use for this. So I mean, this book is really very good to read. So if you find time, you should definitely read this book.
Oh my God! These are the Bibles, road to reality. Have you finished the Bible?
No, not. I mean, I just read about 15-20 chapters, not more than that.
Oh my God! How many? It probably contains 30-40.
No, it's in more than that.
More than that, I think approximately 40. Or anyway.
So then I should not have read about 2020. So maybe I read only 5 or 10. Okay.
It's
So-
exceptional. So I think you can discover almost all.
Thank you, sir. Thank you. So
Thank
this is why
you.
Euclid also said about geometry. There is no royal road to geometry.
I think if this is the title you gave, na, then there is no royal road to LaTeX or royal road to LaTeX. You gave one talk in item class.
Yeah, I mean this is what Euclid told to Ptolemy, but then okay, let me just stop recording it.